Now this is a coupled line directional coupler. It has got edge coupling between the main line. This is the main line where this is the port 1, this is the port 2, and it has got another microstrip line which is coupled to the main transmission line by being slightly edge coupled. The distance between the two transmission line is very small, which allows the coupling of energy between the two transmission lines. The length of the transmission line is kept as quarter wavelength at the design frequency of 1500 MHz. Now we need to find out the parameters of this coupled line coupler. We need to find out the insertion loss, that is the port S12. So we will connect the source to port 1 and we need to connect the receiver to port 2. This will allow us to measure the S parameter S12. As you can see, we had the reference power as minus 40 dBm. Now the power has reduced to minus 40.7 dBm. So the insertion loss S12 is 0.7 dBm. Now we would like to know the isolation of this coupled line coupler. Isolation is S14. So we will connect the source to port 1. We will connect the receiver to port 4 and we will terminate all the other unused ports into 50 ohms. The reference power was minus 40 dBm. Now the power on the receiver is minus 56.6. So 16.6 dB is the isolation of this microstrip coupler. This microstrip coupler has got the design limitations because of the difference in velocities of the odd and even modes. Now we would like to know the coupling factor. For coupling factor, we will connect the source to port 1 and we will connect the receiver to port 3. So S13 is the coupling factor. Reference power was minus 40 dBm. Now the power has fallen down to minus 51. So 11 dB is the coupling factor of this directional coupler. The directivity is isolation minus coupling. So the directivity of this coupler is roughly about 6 dB. The directivity needs to be as high as possible, but due to the design constraint, it's 6 dB with this coupler.